Welcome to Pomodoro Joe for Sunday, February 12th, 2023. Today we're doing LeetCode problem 2477, minimum fuel cost to report to the capital. This is a medium problem. And the problem statement says, there is a tree, i.e. a connected, undirected graph with no cycles. Country network consisting of n cities, numbered from 0 to n-1, and exactly n-1 roads. The capital city is 0. You are given a 2D integer array roads, where roads at I is equal to a I bi, denotes that there exists a bidirectional road connecting cities A and B. There is a meeting for the representatives of each city. The meeting is in the capital city. There is a car in each city. You are given an integer seats that indicates the number of seats in each car. A representative can use the car in their city to travel or change the car and ride with another representative. The cost of traveling between two cities is 1 liter of fuel. Return the minimum number of liters of fuel to reach the capital city. Okay, and then they have some examples and some constraints, I assume. Yep. Okay, everything looks pretty good. All right, so let's take a look at one example here. So in this example, we're trying to get to city 0. Actually, in all the examples, we're trying to get to city 0. So in this diagram, it shows city 0 at the center. And so we can imagine this as city 0 is the center of like a bullseye or a target. And then the first ring outside will be the cities that are directly connected to city 0. Then there's a second ring, and those are the cities that are connected 2 levels out from 0. And then there's a third ring, and so on and so forth. Until we get to the very edge, and those are going to be our, I'll call it a leaf city. It's not quite the same as a leaf in a tree, but it's similar. So a leaf city looks like it only has 1 road that connects it. The other cities all have at least 2 roads that connect to other cities. So if I were planning this as like a carpool coordinator, I think I would look at all the leaf cities first, and then see where they're connected to, move the people to that city, then see where that's connected to, and keep moving in until I get to city 0. So that's my plan. Go to the furthest out city and work our way back. That sounds very similar to a depth first search. You go to the deepest point and then you work your way back. So I think that's our clue to how we should approach solving this problem. All right, with that, we'll put 25 minutes on the Pomodoro timer and get started. So I think the best way to approach this problem will be as a depth first search problem. So we'll start with the generic depth first search, and then we'll modify it to meet the needs for this particular problem. So we'll have some result, set it to 0, and we'll return that result at the end. All right, now we need to implement our depth first search. This will be a recursive function, and this is just going to be our standard depth first search. So we'll define. It'll take some node. And then we'll need to process all of the connected nodes. So for every child node in the connected nodes. So here's our first issue. We don't actually know the connected nodes because we're just given roads. So let's convert these roads into something that's a little bit more useful. So let's turn our roads list into a dictionary of key value pairs, where the key is the node and the value are all the connected nodes. So for that, we will have some nodes default dictionary. And this could be a list or a set. I think for now we'll make it a set. Okay, and then for every road, we will add both nodes to our default dictionary and the connected node. So we'll have A, we'll just call that road. So to be clear, I don't need to break these out into variables. I could just use these directly, but to make it a little bit easier to understand, I'm going to break this out into A and B. So A connects to B and B connects to A. They connect to each other. So our nodes at A, we will add B. And we have to do the same for the other direction. Okay, so now we do have a list of nodes that are connected to any given node. So we can start using it here. Instead of calling this child node, I think I'll call it next node. And for now, I'll just pass. So basically, well, I guess I won't pass. I'll go ahead and call our depth first search. So essentially, we will be calling our depth first search on all of the connected nodes, as long as it's not the node we just came from. So now it gets a little bit tricky. We don't want to go back down a road that we just traveled. So let's have an indicator of which node that is. So we'll call that you can call it the from node, the source node. I'll call it the parent node in this case, or just parent. So as long as our next node is not the parent, we don't want to go back to where we came from, then we'll go down those other roads. So if the next node is the parent node, we'll just skip it. Otherwise, we'll be calling depth first search on our child node. Okay, so this is our basic outline for depth first search. We start at some node, in this case 0, and then we'll look at all the connected nodes, and as long as we're not backtracking, we'll do a depth first search on those nodes. At some point we need to reach the end. The end will be when our connected node has no child nodes. That's going to be this leaf node out here. And then we will start returning and recurse back up. So we'll have some return at some point. We have to figure out what we need to return now. Now we get into the part of the problem that really deals with people and fuel and things like that. Okay, and then out here, we do need to make our recursive call to start the whole thing off. So let's call depth first search on node 0. And we'll set our result to the answer. Okay, and let's see, we are now passing in the parent. So we have depth first search on node 0, and it does not have a parent. So we'll just set that to none. Okay, this is the basic outline for depth first search. Now, how do we handle processing these nodes? Well, what do we know about each of these cities? Well, one thing we know is each city starts with one person. So we'll have people, and they'll start with 1. We also know that they have 1 car. So we have car, that's equal to 1. And we kind of want to know how much gas was used. So a little bit more abstractly, or a little bit more top-down, let's talk about what we're doing. We're getting down to this leaf city. We're going to return up the chain until we reach 0. And every time we return, we'll return how many people are coming from that city, so that when we get back to this city, we're basically gathering all the people from the lower cities into one city before sending them all on to the next city up the chain. So we'll know how many people are arriving into city 3 in this example, and then we'll have to send all of those people up to city 1. So we'll accumulate people, which means that we will want to return our people. What else are we accumulating? We need to know how much gas it took to get those people to the city 3. So from city 2, there's just 1 person. We know it took 1 liter to get them to city 3. In this case, city 3 will have 2 people and probably 1 car. It depends on how many seats. I guess in this case, there are 2, so you have 1 car. So in that case, the gas it took to get from city 3 to city 1 is just 1 car's worth of gas. So we might want to count how many cars are traveling, or we might just want to keep track of how much gas was used. I think in my case, in my head, it makes more sense to use gas. So it took 0 gas to get this 1 person. So at the very start of the nodes, our first node, or every node has 1 person, 1 car, and it took 0 gas to get that person to this node. But for every child node, let's see, it's going to return the number of people that it's sending us, and it's going to return, I'd say, how much gas it took to get these people here. So I'll call this like used gas. And of course, we do need to pass in this node as the parent so we don't backtrack. Okay, so in our case, we need to return people and gas. So how do we update the people and the gas for this node? Every time we get some people from our child nodes, we have to update our people. So in this case, I'll call this new people. So these are the new people coming from our child nodes and the gas that it took to get them here. Now, the people at this node, we add these new people. And the gas at this node, we will add all this used gas. And now, before we return from this, we need to add our people, which I guess we've already done because we started out with people. But now we need to say how much gas it took to get all of these people. So all the people from all our child nodes have gathered in this one node. We have to figure out how much gas it's going to take to send all of those people up to the next city. So let's see, we'll have gas, and then we need to add in, what do we add in? Well, we add in the number of people divided by the number of seats in the cars. So that's going to tell us how many cars we need to get to the next node. And we will actually need to call ceiling on this because we want to make sure that we have, if there's one person, they still need at least one car. So we don't want to round down, we want to round up. Okay, so now that we're returning the people and the gas that it took to get from our child nodes, we'll pass that on up to our next node. All right, so I think that just about does it. Now the only problem that I see here is at the end, when we get to our 0 node, I think we'll be sending our 0 persons, so our gas, unfortunately, because we're adding this in at the end, when we return our 0 node, we'll also add all of the people that it gathered, plus it's kind of like this circular loop where it's 0 node people are all traveling back to 0 node because we've added this gas. So for each one of these nodes, we're saying this is how much gas it took to get from this node to the next node up the chain. But when we get to node 0, we're still saying that it's going to take all the people at node 0 plus some number of cars to get to node 0, which is not really what we want. We could say something like, well, if we're node 0, we just return, but I think it's easier to say, let's just subtract this sort of incorrectly added gas at the end. So in this case, it will be let's see, I guess in this case also our result isn't quite right because our result is really broken down into 2 pieces. We're returning both people and gas. So now we'll subtract the same ceiling of people divided by seats. And then our result will equal this. We can actually just set result is equal to the gas minus this extra added gas that we didn't really need. Okay, that's a little bit ugly. I don't like this fact that we have to subtract this gas out at the end. There might be a way to handle that better, and it looks like we don't need this cars at all because we're just keeping track of gas. All right, let's run this. I'm running low on time, so let's just run this and see if it works. So that works. Let's run this and see how well it does. And we do pass. It's not great. It only beats 33% for runtime, and it only beats 9% for memory. So not the best solution. If I were to do this over again, I would probably not use a recursive algorithm like this. I might search out our leaf nodes first. And you can find a leaf node just by looking for any node that only has one connected node. So find the leaf nodes first, process all those leaf nodes, push those people up to the parent nodes. It'll be a very similar algorithm to the depth first search, but you could do it in an iterative way. So you grab all the people at the lower node, push them up to the higher node. I might even keep a single dictionary or a single array of how many people are at each node, and then push them up to the next node, and finally push them up to 0. Okay, well, I think we have a fairly decent solution that's fairly easy to understand. The only sort of ugly bit is this resulting gas that we had to delete. Maybe you can improve upon this. I bet you can. So that's a challenge for you. This is, again, LeetCode 2477. Check this out. Try to beat my score. I dare you. All right, hope you had fun. Hope you learned something. Hope you enjoyed this. Hope you can go out and write better code.